Hello, welcome back to the channel. So let's continue our discussion on comparison test and check whether this improper integral converges or diverges by only using comparison test. So if you have not watched my previous videos on comparison test, I'll highly suggest you to first watch my previous videos in order to get the full context of this video over here. So you know that when we have to use comparison test, we always come up with a second function for which it is easier for us to calculate the integral of our second function rather than calculating the integral of original function, right? And you can clearly see in this case that since this is a complex integral, our original function in this case is basically 1 over x squared plus root x, right? So if this is the case and we have to come up with an easier function for which we already know the integral for, you know that by comparison we can either take our g of x to be 1 by x squared or our g of x to be 1 by root x in this case, right? Because we know the integral for both of these functions and both of these functions are indeed simpler than this expression over here, this original function, right? So you know that we can definitely go with these two functions over here, and you'll clearly notice in this question that you'll have to eventually use both of these functions to check whether this integral converges or diverges. So now since we have clearly identified our f of x and g of x functions, let's compare our f of x and g of x and check which one is greater. And you also know that we also have to check those comparisons based on the interval provided in the definite integral. So now since we have clearly identified what our f of x and g of x are, let's compare both of these functions f of x and g of x and see which one is greater, right? Or which one is smaller. But before doing that, in the f of x original function expression, you can clearly see that when your x is large, your function behaves like 1 over x square in this case, right? If your function is large, x square dominates over root x, right? But if your x is small, since you are concerned with all the values of x greater than or equal to 0, you know that when your x is in between 0 and 1, root x dominates over x square, right? So that is why we'll have to use both of these functions to drive the comparison test. So since we are concerned with all the x values greater than or equal to 0, we know that for the values of x in between 0 and 1, our root x dominates over x square. So we'll go with 1 by root x in that case. And also when our x is greater than or equal to 1, our x square dominates over root x, so we'll go with 1 by x square in that case. So for this integral, what we will do is, for the original integral, we'll split this integral over here. So what we'll do is, we'll write the integral, the original integral, as simply integral from 0 to 1 dx over x square plus root x plus integral 1 to infinity dx over x square plus root x. And we only did that because we had to come up with a reasonable guess for our g of x function. So for a reasonable guess of our g of x function, we'll have to split this integral into two parts such that we have a reasonable guess for our first part, which is 1 by root x, and for our second part, a reasonable guess which would be 1 by x square. And you know that in both of these cases, if you compare 1 by x square plus root x with 1 by root x first for this integral, if you compare that, you'll notice that your 1 by root x is always greater than equal to your first expression, and both of these expressions, since your x is in between 1 and 0, you know that both of these expressions are also greater than or equal to 0, and that is what you also need for the comparison test. So you know that basically your g of x is greater than or equal to your f of x is greater than or equal to your 0 for your first integral case, and if you'll compare 1 by x square plus root x with 1 by x square as well, you'll notice the same inequality over here. Since in this case as well, when your x is greater than or equal to 1, in this case, since your denominator on the left hand side is larger than the denominator on the right hand side, so that is why your original expression on the right hand side is greater than equal to your original expression on the left hand side. And also in this case, since x is greater than equal to 1, x is taking positive values, both of these expressions are also greater than equal to 0. And again, in this case as well, you have the same inequality equation. G of x is greater than equal to f of x is greater than equal to 0 in this case. And now based on these two inequalities, we know that these inequalities clearly satisfy the first case of our comparison test. So we know that our g of x, which is our second function, in both of those cases is greater than equal to the absolute value of f of x. Since we know that our f of x is always positive, our f of x was always greater than equal to 0, right? So it doesn't matter if we take the absolute value of f of x or just f of x in this case, because of these two inequalities over here, right? You know that your f of x is always greater than equal to 0. So it doesn't matter if you take the absolute value of f of x or the original f of x value, right? So we know that our inequalities clearly satisfy this equation over here, and if we are able to prove that our second function integral converges, we'll also prove that our original function integral, which is this expression over here, will also converge. So what we have to do is, since we are comparing this expression over here, we know that integral of 0 to 1 of dx over x square plus root x is less than equal to integral of 0 to 1 by root x dx, and also integral from 1 to infinity dx over x square plus root x is less than equal to 1 to infinity of 1 by x square dx, right? Because of these inequalities over here, these two inequalities over here. So now since we have these two inequalities over here, let's check about the convergence and divergence of these two integrals over here. And if you'll clearly identify that we have already solved these type of questions before, if you'll calculate the integral of this expression over here and also the integral of this expression, you'll see that both of these definite integrals have a real solution to them. So if both of these definite integrals have a real solution to them, so you know that both of these integrals converge, right? So now if both of these integrals converge, we know that this combination of two individual integrals will also converge, because we proved that this integral converges by proving that this integral converges, and we also proved that this integral over here converges because of the convergence of this integral over here. So since both of these integrals converges, it means that our original function integral also converges. And that is what we concluded by only using comparison test and not solving this improper integral over here and then finding a solution to it, right? So that's it for this video. Again, feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.